The first thing that we can do with the linearized Einstein equations that we obtained in the previous video is to try to solve them in the simplest case, just as you try to solve the equations of for the electric field in the presence of a charged point particle and you get a Coulomb solution. Here you want to solve these equations for a massive point particle at rest at the origin, and you will get something which you can think is analogous to the Coulomb solution. So we need the word line of this point particle, okay, and we prefer to have it parameterized by the proper time, and it is just given by s and 0. Okay, is this correct? Oh, well, one way to check it is to compute x dot mu, which is the derivative with respect to s. In this case, this gives us, okay, this would be the vector 1, 0, and eta mu x dot mu is just 1, as you expect from a massive particle. So this is okay. The equations that we want to solve are these in the Donder gauge, which has the simplest, gives the simplest form of the equations. Okay, where this T mu nu will be the energy momentum tensor of the particle, but which energy momentum tensor? We said that has to be the Rosenfeld one. So it's the gravitational energy momentum tensor with the metric replaced by the Minkowski metric. So now let's go back to the place where we computed the energy momentum tensor of the particle. And remember that this was given by minus mc squared integral ds delta 4 x minus x divided by square root of g x dot mu x dot nu. Now, if we want the Rosenfeld one, this means that we have to replace the metric by the Minkowski metric that has determinant equal to minus 1. So square root of the absolute value of the determinant is 1. So this is removed. Then, well, we just computed these x dot mu's. They are delta mu 0 and delta mu 0. So this energy momentum tensor only has vanishing components t0, 0. And finally, we have to find what to do with these deltas. Okay, this delta 4 can be split into delta 4 x0 minus capital X0, sorry, just delta, and delta 3 x minus capital X. But this capital X is 0. This is what happens for this word line. This capital X0 is just S. Okay. And we have T mu nu 1 minus mc squared okay, this integral just gives us 1 and then delta 3 of x delta mu 0 delta mu 0. So I put this result in a box. This is minus mc squared delta 3x delta mu 0 delta mu 0. This is basically the result that you expect. This is energy concentrated, mc squared, units of energy concentrated at the origin, and the sign is because of our conventions I have explained several times. Now let's go to this equation, and we have d squared h bar mu nu equal to minus chi over c mc squared. So this square goes with this c delta 3 then of x delta mu 0 delta mu 0. This is the question that we want to solve, and since the source is static, it is natural to expect this h bar to depend only on spatial coordinates. So we assume that the t h bar mu nu is 0, and in this case this D'Alembert becomes minus di, just the Laplacian of h bar mu nu. Okay, these two signs now cancel. Let me write the whole thing. mc delta cube x delta mu 0 delta nu 0. And well, we can assume that the only thing that needs to be solved is that has a non-trivial solution is h bar 0, because this is the only non-zero component, h bar 0 0, because this is the only non-vanishing component of the source. We know that the I of 1 over r is equal to minus delta 3 of x and 4 pi. Okay, this is the equation that we need to remember, and this means that okay, h mu nu will be minus 1 over sorry, let me put this constant here, chi mc, then all these divided by 4 pi and 1 over r delta mu 0 delta nu 0. So this is automatically the solution to this equation, because h bar mu nu is defined as h mu nu minus half eta mu nu h. Well, it is simple to find that h mu nu is given by h bar mu nu minus a half of eta mu nu h bar, where h bar is just the trace of h mu nu bar, just as h is the trace of h mu nu. So let me write it explicitly. This is eta mu nu h bar mu nu. Since well, and now we know h bar mu nu, we can compute h bar, and then we can compute h mu nu, which is what appears in the metric at first order in chi. Okay, let's compute h bar. So h bar is just eta mu nu, h bar mu nu. Since h bar mu nu only has component 0 0, this is just h 0 0, which is what we wrote above. Then we come here and we compute h mu nu is minus chi mc divided by 4 pi 1 over r delta mu 0 delta nu 0 minus half eta mu nu and this, so it is plus chi mc divided by 4 pi 1 over r. This is the result, and probably now we want to write this, write the components, because we will get some simplification. So h 0 is minus chi mc divided by 4 pi 1 over r plus a half of the same, so you have minus 1 over 8 pi, and now the components hij, the only ones that now matter, the contribution comes from here, and it would be minus delta ij from eta mu nu. So it is minus chi mc divided by 8 pi 1 over r delta ij. Okay, we're almost there, and we need to make some definitions. Let me call c squared times chi divided by 2h0, which is minus gm over r. Okay, there is a chi here, there's a chi there. Remember that chi was 16 pi g over c squared. Okay, so this whole thing is just this, and we call this phi. Remember that this is just the gravitational potential created by a mass at the origin according to the Newtonian theory of gravity. So with this definition, we find that hij, or if you want c squared k power 2 hij, is just phi delta ij. Okay, almost there. Now we have that g00 is eta 00, which is 1, plus chi times h00. So chi 00 is just 2 times phi divided by c squared. And gij is eta ij, which is minus delta ij, plus again chi times hij, but this is 2 times phi divided by c squared delta ij. And we can take a common factor. Okay, prefer to do it like this, minus 1 minus. Okay, this is the metric to first order in this chi, or at a linearized order. If we write it like this, then we find this form. Okay, and this is times c squared dt squared minus 1 minus 2 phi divided by c squared, and delta ij times dxi dxj, which is the x squared. Okay, and here we are. Now remember that we obtained this part of the metric. We guessed that we showed that in the non-relativistic limit the potential could be obtained from a metric if we modified the Minkowski metric adding this piece. Okay, and then we showed that this was part of some metric to which we gave a name, and that it was what one obtains what an accelerated observer sees in a Minkowski space-time. Since this was equivalent to Minkowski space-time, well, the metric was flat and the curvature was different from zero. Now what we are showing is that in this there is an extra piece here, and this is telling you that the curvature, okay, is different from zero, and that there is a non-trivial gravitational field. We should remember this expansion. Okay, this is one of the important formulas of this course. So that this term for a point particle to this order is given by 1 minus 2 gm divided by c squared, and all this divided by r. This constant here is the Schwarzschild radius. And also this expression is important because if we look at, suppose that you have some mass distribution, a star, a planet, somewhere, but you are looking at this mass distribution from very, very far away. So this mass distribution looks like a point at a certain distance, and also the gravitational field is very weak. You expect the metric to be approximated by this form. And if it is approximated by this form, you just need to read this coefficient here to find what the mass of the object that produces this field is. Okay, so this calculation is important for these two reasons.